Hello guys, today in this class I'm going to discuss about the mechanisms of redox reactions in coordination complexes. And previously in the previous lecture I talked about the mechanisms of racemization reactions in triskeliate complexes. And this is another mechanism that this talks about the redox reactions in coordination complexes. And let's see what's a redox reaction. Redox reactions are nothing but electron transfer reactions, and an electron or more than one electron transfers from one species to another species. That's basically one reactant to another reactant. The reactant that gives away electron or the reactant that loses the electron is called a reducing agent, and also it is called reductant. And similarly, the reactant that accepts the electrons or that gains the electron during the course of the reaction is called oxidizing agent or oxidant. Oxidant, that is the correct way of saying. Yeah. Now let us see how many types of mechanisms are there in redox reactions in coordination complexes. There are two types of mechanisms known for the redox reactions in coordination metal complexes. One is outer sphere mechanism, another one is inner sphere mechanism. And I'm going to talk in detail about both the mechanisms. First, let me take the outer sphere mechanism. In the details, that is basically the minute step-by-step the course of the reaction, how it's going to happen in this outer sphere mechanism. O stands for oxidant and R stands for reductant. And here you can see that actually the oxidant and the reductant come closer and form a precursor complex. Just a second. Here, this is the oxidant and this is the reductant. And they come closer and form a precursor complex. This is called a precursor complex. And in this precursor complex, the distance between the oxidant and the reductant is good enough for an electron transfer to occur. But that's not enough for an electron transfer to happen. So now what is going to happen is this precursor complex further forms an activated complex. In the activated complex, all the energetics have been worked out for an electron to go from the reductant to the oxidant. And once the activated complex has been formed, the one electron goes from the reductant to the oxidant, and oxidant gains one electron and reductant loses one electron. Now once the electron transfer occurred, then the activated complex dissociates into individual complexes. This time the individual complexes, that is the oxidant, goes with one electron and one extra electron, that means, and the reductant goes by losing one electron. So the finally what's happening, we started with oxidant and the reductant, and then finally we ended up with O minus and R plus. So during the course of the reaction, what's happening is the the oxidant gains one electron and the reductant loses one electron. Now I'm going to take an example and explain in detail. In this example, we have an iron 2 complex and iron 3 complex, and here you can see, just a second, yeah, this is iron 2 complex, sorry, this is an iron 3 complex and this is iron 2 complex. And then what's happening is an electron transfer is taking place from iron 2 to iron 3. Then iron 2 becomes iron just a second, iron 3, and iron 3 becomes iron 2. Okay, that's what is happening. Basically, in this reaction, both the products and the reactants are the same, but only the difference is that one iron atom or the ion is isotopically labeled, but that's not going to change the reaction at all. Anyway, now for such an electron transfer to take place, one may think that actually there is no need for input of energy, but basically it requires 33 kilojoules per mole for this reaction to happen. That is the activation energy that is required. But how? Why do we need to input energy for this reaction? But as I mentioned in the previous slide, for an electron transfer to occur, you need to bring oxidant and the reductant closer, so that that's a suitable distance for an electron transfer to occur. And in addition to that, the energetics to be worked out. So what are the energetics? So Frank quantum principle says that the electron transfer can occur from one orbital to another orbital only when they have the same energy. That electron transfer occurs without the input of energy, only when these orbitals are having the same energy. But if you take a look at iron 2 and iron 3 complexes, the orbitals here, for example T2G orbitals, are not having the same energy. The T2G orbitals in iron 2 complex are higher in energy, and T2G orbitals in iron 3 complex are lower in energy. So the electron transfer cannot happen from one orbital to another orbital without input of energy. So now what's going to happen here is, since the energy of the orbitals depend on the bond length, so the bond length adjustment is going to take place. The bond lengths in iron 2 complex are longer than those of iron 3 complex. So what's going to happen here is the bond lengths of iron 2 complex are going to become shortened, and the bond lengths of iron 3 complex are going to elongate. But anyway, that we're going to discuss in a pictorial representation that I'm going to show it to you. But basically, the activation energy of 33 kilojoules per mole is required for this reaction to happen. But this activation energy is not just only the energy required for bond length stretching and elongation, but it is composed of three components. We're going to take a look at that. That's delta G double dagger is composed of delta G double dagger T, delta G double dagger I, delta G double dagger A. So what are those three terms? The first term, that is delta G double dagger T, is the energy that is associated with the bringing two reactants, that is the oxidant and the reductant, to bring closer. That means that actually you need you need to do work in order to bring these two together, these two reactants closer. So if the complexes are charged, for example, in this example, iron 3 is having a +3 charge on the complex, and the iron 2 complex is having a 2+ charge on the complex. So they repel. So in order to bring them closer, so you need to overcome the Coulombic repulsions also. So the energy required to bring these reductants and the oxidant closer, so that is the delta G double dagger T. And then delta G double dagger I, this is related to the energy required for stretching and the shortening of the bonds in these complexes, so that the orbitals come to the same energy level and electron transfer can happen. Okay. Now delta G double dagger A. What is delta G double dagger A? This is related to the reorganization of the solvent molecules around both the oxidant and reductant. For example, what do you mean by the reorganization of solvent molecules? See, for example, you have iron 2 complex. The first coordination sphere is here. You have hexa, aqua complex. So therefore you have water molecules surrounding the iron 2+ complex, and there will be solvent molecules around this coordination, the first coordination sphere. So for iron 2 they will be different, for iron 3 they will be different. So the reorganization of these solvent molecules, once after the electron transfer takes place, even before the electron transfer takes place, needs to be arranged so that when the bond lengths in iron 2 and iron 3 change, the environment of these solvent molecules also change. So for that you need to have input some energy. So all these three energies, that is, the first one is for bringing the oxidant and reductant closer to each other for an electron transfer to occur, and for the second one is for the making the bond length equal, so that the energy of the orbitals become equal. And the last one is the reorganization of molecules, that is the solvent molecules surrounding the first coordination sphere. Yeah, now let us take a look at the pictorial representation of how these bond lengths are going to change. And this one is the iron 2 complex, and this one is the iron 3 complex. So now you can see these are just a representation of the bond lengths, and then iron 2 has the longer bond length and iron 3 has shorter bond lengths. And now in the activated complex, both iron 2 and iron 3 will have the same bond lengths. You have the same length here. So when the bond length becomes same, so what happens is the energies of these two orbitals, the energies of the orbitals involved for the transfer of electron, they become same in energy. I mean, the energies become same. So once the energies of the participating orbitals become the same, the electron transfer takes place. Once the electron transfer takes place, then the here it is supposed to be iron 3, so it's a typo. So this is iron 3. So the iron 3 goes with the shorter bond length and iron 2 goes with the longer bond length. And let's see one thing. For example, if the electron transfer is happening without the stretching or the shortening of the bond length, that means that there is no alteration of the bonds in iron 2 and iron 3, for example. Then the electron transfer takes place, and then you will end up with iron 2 with iron 3 bond length and iron 3 with iron 2 bond length. And then finally what's going to happen? When they relax, they're going to release energy, which is actually against the, you're not actually you have not done, you're not supplied any energy. That means there is no input of energy, but when they relax, they're going to give you the energy. So that means that it is against the fundamental laws of thermodynamics. So basically the input of energy is required. Now take a look at the activation energy versus the bond length differences. If the bond length differences between the reductant and the oxidant is high, then what happens is the energy required for bringing them to equal length is going to be high. So that means the activation energy is going to be high and the reaction is going to be slow. And in this type of mechanism, so far you have seen that no bonds are broken and no bonds are made. Here we have two examples of self-exchange reactions. A self-exchange reaction means if an electron transfer takes place between different ions of the same metal, that means that iron 2 to iron 3, cobalt 2 to cobalt 3, then it is called a self-exchange reaction. And if an electron transfer takes place from, for example, iron 2 to molybdenum 5 or some other metal to some other metal, then we call it a cross reaction. Now here we have two self-exchange reactions, and what is important is the rate constants of these two reactions are entirely different. Though the ligand is the same and it's only one electron transfer is taking place in both cases, the cobalt couple, the reaction of the cobalt couple is 10 to the power of 8 times slower. Take a look at these rate constants.
10 to the minus 6 and 10 square. So that is basically 10 to the power of 8 times slower. The cobalt couple is slower than the ruthenium couple. And then why? And if you take a note of the bond lengths in case of the cobalt couple and the ruthenium couple, you will see that the difference in the bond lengths in case of cobalt couple is much larger than the ruthenium couple. And if you take a look at this, the cobalt nitrogen bonds and the cobalt nitrogen bonds in the trivalent, the difference in the bond lengths is 0.178, and in case of ruthenium couple it's just only 0.04. So what does it mean? How is it related to the bond length? I mean, the bond length difference, how the bond length difference is related to the rate of the reactions. We talked in the previous slide that for an electron transfer to occur, the bond lengths have to become equal in a self-exchange reaction. So if the bond length difference is high, then more energy is needed for them to become equal. But if the bond length difference is less, then the energy required for bringing them to the same length is less. So that means that activation energy will be higher in case where the bond length difference is high, and in the other case where the bond length difference is low, the energy of activation is less. So when the energy of activation or the activation energy is high, then the rate constant is going to be very, very low. So that's what is happening here in case of cobalt couple. In case of cobalt couple, the bond length difference, that is a cobalt nitrogen bond length difference in case of divalent and trivalent ions, is 0.78 angstrom units, and the bond length difference, that's ruthenium nitrogen bond length difference in between the divalent and the trivalent ruthenium is just only 0.04. That's very less. So this bond length difference makes a lot of difference in the activation energy. Yeah. And now it is not always true that actually the cobalt complexes, or I mean the electron transfer in all cobalt complexes is sluggish or slow. It's not true. In case of, if you take a look at this couple, cobalt 3 and cobalt 2 couple again, but with phenanthrene ligands, the reaction rate is quite good. It's not in negative denominations, but it is actually, it is rate constant is 40 per mole per second. It's quite high compared to the compared to this value. So why is it like this in this case? In this case, the phenanthrene ligand has pi system, and the ligands with a pi system can pass electrons easily from one metal to the other metal. Ligands with pi systems provide easy passage of electrons. So that's the main reason why the rate constant of this reaction is high. Here is the Marcus equation. This gives a relationship between the rate constant of a cross reaction to its equilibrium constant, and also to the rate constants of individual self-exchange reactions. Let me explain you the terms the Marcus equation, as you see, that it is K12 equals to K11, K22, K12 and F12 to the power of half. And you can see that actually what is it? K12. K12 is the rate constant of the cross reaction. K11 and K22 are the rate constants of the related individual self-exchange reactions. And K12 is the equilibrium. K12 here, actually K is a capital, and K12 is the equilibrium constant of the cross reaction. And let me explain you what, basically by taking an example, I'll explain you what the Marcus equation is, how we can, how useful it is. Take a look at a cross reaction. Here we have iron in +2 oxidation state and molybdenum in +5 oxidation state in the reactants. Then now iron 2 gives an electron to molybdenum 5, and iron becomes iron 3, and molybdenum becomes molybdenum 4. And in this cross reaction, there is an exchange of electron. That means a transfer of electron from iron to molybdenum. And the equilibrium constant for this reaction is 1 into 10 squared. That means it's 100. Rate constant for this reaction is the one which we are going to find out by using Marcus equation. How do we find out? To know the rate constant of this cross reaction, we need to know the rate constants of two individual related self-exchange reactions. Self-exchange, that means that actually in this cross reaction, iron 2 is becoming iron 3. So now we need to know the self-exchange, the rate constant of the self-exchange reaction of iron 2 and iron 3 with the same set of ligands. So here you have hexacyanide complexes of iron 2 and iron 3, and an electron transfer takes place from iron 2 to iron 3 in the first reaction. In this case, here you have iron 2, and this one is in +3 oxidation state, and this iron 2 becomes iron 3, and iron 3 becomes, iron 3 becomes iron 2. This is a self-exchange reaction. The rate constant for this reaction has been found to be 7.4 into 100. And another self-exchange reaction in which the molybdenum 5 is becoming molybdenum 4, and then 4 is becoming 5. So in this molybdenum couple, the rate constant for this molybdenum couple is 3 into 10 to the power of 4 per mole per second. So now we know the rate constants of two individual self-exchange reactions, and all we need to know is F12. F12 normally is 1 if F12 is not given in any problem, then you take it as 1. If F12 is given, then you can use that value. So now F12 is given as 0.85. So you can take this value, and if you take all these values and substitute in Marcus equation, and you will get this value. This is the calculated rate constant for the cross reaction. This is the where is the cursor? Okay, this is the cross reaction. The rate constant for the cross reaction is, that's a 4 into 10 to the power of 4 mole per second. And experimentally what has been found is actually 3 into 10 to the power of 4, which is pretty much close. So this is how actually Markow's equation has been found to be very useful in predicting the rates of the reactions in the cross reactions in outer sphere mechanism. And the confidence on the Markow's reaction is such that if the calculated and the experimental values do not correlate, then it has been considered that the reaction does not undergo via outer sphere mechanism. So such is the confidence on Markow's equation. Now I'm going to talk about excited state outer sphere electron transfer reactions, and let's take an example of ruthenium tris bipyridine complex. And here we have just a second. Yeah, here we have the classic example, ruthenium complex, and when this complex absorbs the electromagnetic radiation of 452 nanometer wavelength, it goes to an excited state, which is typically a very short-lived one, and then it undergoes this species undergoes radiation-less decay to give an excited state, this one. And it's very interesting to note the redox properties of this species. So what's happening during the excitation is that an electron from ruthenium is promoted to the antibonding orbital of one of the bipyridine systems, pi systems. That means that actually an electron is going from ruthenium to one of the bipyridine ligands. So that is basically a charge transfer transition, and this is happening from metal to the ligand. So this is an MLCT, metal to ligand charge transfer, is the one which is taking place here. And since this one, in this case, in this excited state, the electron, the one which is promoted to the antibonding orbitals of one of the bipyridine, is not actually residing with the ruthenium. It is there, the antibonding orbital of the bipyridine. So therefore we can write the formula like this: ruthenium 3 and BPY twice and another BPY with negative charge, and of course the overall charge on this remains the same, that is 2 plus. So you have an additional electron on one of the bipyridine ligands, and there is a hole. That means that there is a loss of electron in the ruthenium. That changes the redox properties of this excited state complex tremendously. And now let us compare the redox properties of this excited state with the ground state complex, that is this complex. Now first let's look at the reducing properties. Reducing means the complex is reducing something else. That means that complex is giving away an electron to something else. So now here, and then by giving away one electron, the ruthenium 2 plus, this one here you have +2 oxidation state, and ruthenium 2 plus becomes ruthenium 3 plus. So that means that we are interested in this reaction. So that is from here to here. So when you reverse the arrow, then you need to reverse the sign. that is 1 point minus 1.26 volts. And then now take a look at this case, and here also it is ruthenium 2, and here it is going to become like this. So that means when we are interested in this reaction, here it becomes 0.86. So that means that this reaction is feasible, and this reaction is not feasible unless you input 1.26 volts of energy. So now you can say that this is a that is a excited state ruthenium complex is a better reducing agent than the ground state complex by how many volts? That is 0.86 plus 1.26 volts. So that is 212, that's a 2.21 volts. So that is the conclusion. That is, the excited state ruthenium complex is a much better reducing agent than the ground state ruthenium complex, because you see 2.12 volts is not a small voltage. Okay, now let's take a look at the oxidizing properties. Oxidizing property means that the ruthenium complex, this complex, is accepting the electron from something else. So that is oxidizing something else. Oxidizing something means then it is taking electron. So by taking electron, ruthenium 2 plus becomes ruthenium plus. So that means that actually we are interested in this reaction. So ruthenium 2 is becoming ruthenium 1. That is, here we have ruthenium 1. And here it is ruthenium 2. So this is not a spontaneous reaction. You need to input 1.28 volts. Then here, take a look at the excited state complex becoming ruthenium 2 complex becoming ruthenium 1. So this is spontaneous, and when the excited state ruthenium 2 becomes ruthenium 1, and there is a release of 0.84 volts, and here we need to input 1.28. So basically you can say that actually the excited state ruthenium complex is much better oxidizing agent than the ground state complex. By how many volts? Again here 0.84 plus 1.28. So that gives you 2.12 volts. So the excited state ruthenium complex is better reducing oxidizing agent than the ground state ruthenium complex by 2.12 volts. So why? How is it possible? Here in this we have written the structure of the excited state complex this way: ruthenium 3, BPY twice, and BPY minus. There is an electron in the antibonding orbital of one of the bipyridine ligands, which makes this compound a better reducing agent, because an electron from this antibonding orbital can be easily removed, so that can be given to any other oxidizing agent. So therefore that makes the presence of an electron in the antibonding orbital of one of the bipyridine ligands in this complex makes it a better reducing agent. And here, since one electron from ruthenium is given to bipyridine, so ruthenium, we can say formally it has +3 oxidation state, or you can say that there's a hole in the ruthenium. So that makes this complex a better oxidizing agent, because by having a hole in the ruthenium, it has a greater electron seeking capability. So that is how the excited state ruthenium complex is a better oxidizing as well as better reducing agent compared to the ground state ruthenium complex.